All right, so whenever you go from NADH to NAD plus, you basically kill the resonance in the NAD plus structure. And so what that leads to happening, right, is that this NADH will really wants to go back to NAD plus. And so, yeah, you kill the resonance, and then it wants to donate those electrons back so that it can regain that resonance. Okay, one thing that we are supposed to know is structured ATP, right? You should be able to draw this by now. I really hope that you've been practicing because OH, H, do. And then goes to N, do, and then NH2, and an N here, and an N here. All right, structure of ATP. That is definitely going to be a question on the exam. Remember that this is the gamma, I believe. This is the beta. This is the alpha. We also remember that the ATP plus water to ADP plus inorganic phosphorus, that has a delta G standard of 30.5 kilojoules per mole. With that, and then there's also the reaction that is ATP plus H2O goes to AMP plus pyrophosphate, which that delta G not standard is 45.6, I believe, kilojoules per mole. Don't quote me on that. We don't actually have to know this one. And I believe there's also the pyrophosphate to 2-phosphate, which that has like a delta G, not prime, of like 15 kilojoules per mole. All right. So we can couple these reactions to energetically unfavorable reactions and make them favorable. Okay. So we talked about where the stability of this, or where this delta G comes from. Right, there is one, the resonance. Right, you have more resonance states in the, like this. Right, you got 4 resonance states with the inorganic phosphorus, and you've got more resonance states with the ADP. Right, so you have more resonance states. You can spread out this negative charge that's here and here and here. And so you can get a lot more, you can get a lot of delta G out of that. There's also the fact that in like an ATP, right, you have, I'm just going to do adenine, and then bloop, 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 OH, right, with the inorganic phosphorus, inorganic phosphorus, inorganic phosphorus, negative, negative, negative. These negatives don't like each other, right? And so whenever you break this off, you can sort of separate that charge, and that gives you electrostatic repulsion. Okay, and then finally, our last one is solubility. right? This inorganic phosphorus here is a lot plus the ADP, right? That's two different sites of solubility, or like, but both of these are more soluble separate than they are in ATP, right? And so it's favorable in an aqueous environment. All right. Okay. So we have a couple reactions to note. There is a couple enzymes that he talked about at the very beginning. Pyrophosphatase. That takes a pyrophosphate and then basically one way converts it to two phosphates with like a delta G naught prime of like negative 19.28 kilojoules per mole is what I have written down. Oh, it takes that, adds a water to turn into two phosphates. There's the nucleotide diphosphate kinase. So nucleotide diphosphate kinase, which takes an ATP plus and any nucleotide diphosphate and turns it into ADP and NTP. All right, so plenty of, so those are some of the reactions. There is the adenylate kinase, which takes two ADP in an equilibrium reaction. I should probably put this as equilibrium here. Takes that and turns it into an ATP plus an AMP, right? And that's why we use AMP as the indicator for low energy, is because of this adenylate kinase reaction. And then we also talked a little bit about thioesters and about how they're high energy compounds, but we don't really have that much there. And then we talked a little bit about NADH and stuff, but I can't really see him asking too many questions on that, especially because we haven't done the Krebs cycle yet, and that seems like a Krebs cycle thing. All right, with that being said, let's go ahead and talk about glycolysis. Glycolysis, yeah. Okay, glycolysis. So we've got two stages, right? We've got the energy investment and then the energy recovery stage, right? This is where we lose 2 ATP. This is where we gain 4 ATP for a net profit of plus 2 ATP in glycolysis. Right, so big picture reaction. We have a glucose goes in with two NADHs, or NAD plus, sorry, and then 2 net ADP and 2 phosphates to give us, I'm going to actually write that down here now. We get 2 pyruvate plus, so we get 2 pyruvate plus 2 NADHs, which can be a problem if we don't get rid of them. 2 ATP, which is always nice. And also 2 waters and 2 protons, but We don't really care. What we do care about is the fact that this does generate protons, so it makes the cell more acidic, right? So acidity increases as glycolysis goes about. If you remember, we talked about hemoglobin. Hemoglobin goes towards or releases the oxygen in the places that are more acidic. Well, the places like this that are more acidic are the places that more reactions are going on. Glycolysis is happening. All right, with that being said, let us go to the first reaction of glycolysis. So the first reaction of glycolysis, we take a glucose to a glucose 6-phosphate. This is done by hexokinase. And in everywhere but the liver, it's done by hexokinase. But then in the liver, it is done by glucokinase. If we remember, hexokinase, CHEM is less than glucokinase. CHEM, right? And that's because, and then that means that hexokinase is more efficient than glucokinase, which, is to be expected. Liver is not really wanting to make a bunch of energy. Liver is wanting to store glucose. And so it's not going to use glucose if you don't have a lot of it in your bloodstream. Excuse me. Okay. Hexokinase, right? So all kinases, the way they work is, and this also has the addition of an ATP to ADP. So this is the first of our ATP investment sites. Okay, so hexokinase, it is a kinase, right? Anytime we see a kinase, that means it's going to need a magnesium ion. And that magnesium ion, what it's going to do is it's going to take this magnesium 2+ is going to take, when the ATP is in the active site, O, P, O, 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 right? And then, you have your whatever is coming to attack this and get the phosphate group on it. Sorry, O, R. Usually it's an HOR. Whatever's coming to attack this, right? The magnesium will help stabilize it help stabilize the negative charge, right? By being there and kind of telling it to chill out. All right, so that is how hexokinase works. It is inhibited by G6P, right? After the next reaction, that'll make sense why it's inhibited by G6P. But for right now, it has product inhibition, and it's not allosteric. It is actual product inhibition where G6P just doesn't leave the active site, right? It'll go into the active site, won't leave for a bit, and so it'll make it work at less efficiency. All right, second step of glycolysis. We have an equilibrium between G6P and fructose 6-phosphate, right? This is done by phosphofructoisomerase. Phosphofructoisomerase, right? Makes sense. Or sorry, phosphogluco. I believe, yeah, phosphoglucoisomerase. Yeah, phosphoglucoisomerase. So phosphoglucoisomerase, what that's going to do is either turn G6P into F6P or F6P into G6P. If we end up with a backlog of F6P, right, some of it's going to turn back into G6P, which is why hexokinase is inhibited by G6P, right? That's why it's inhibited by its product, because if you have a backlog of 6P that's not getting turned into the next one, then you're going to want to have your enzyme inhibited, so you're not making even more G6P and taking glucose away from the rest of the body, right? Because G6P locks in cell, right? So G6P locks the glucose within the cell. Make sure that it is going to do some kind of reaction, but within the cell. And you have to get rid of that phosphate group to not have it do that, which we'll see later. Okay, so G6P to F6P, phosphoglucoisomerase. Not much more to say here. This is a pretty standard one. We turn it to fructose 6-phosphate for later on whenever we do the aldolase step. But that being said, let's go to the next step. Next step, we turn S6P into fructose 1,6-bisphosphate. All right, fructose 1,6-bisphosphate. This is done by phosphofructokinase. The kinase tells you that it's going to turn an ATP into an ADP, which makes sense, right? Because you're adding another phosphate to this fructose, and so you're going to need to get that phosphate from an ATP. This reaction is one way. This is the major control point. For glycolysis, there is quite a lot of inhibition that goes on with this one. So when it comes to regulation of PFK, which is what we're going to call it, phosphofructokinase. Phosphofructokinase is, let me see if I can do this. So phosphofructokinase, right? It is activated by so it's activated by AMP, right? And you think why AMP? Why not ADP? Well, ADP doesn't. AMP is the reason for this is because of the adenylate kinase reaction we talked about earlier. How 2 ADP goes to an ATP and AMP, right? You increase this, or you increase ADP concentrations by like 10%. This increases AMP concentrations by about 400%. So just because of the KEQ of this reaction, that happens. And because AMP levels are usually pretty small, a small amount of ADP means that you get a large amount of AMP. So it makes sense, right? And this AMP activation is like, woo, woo, woo. And then it is inhibited by ATP. ATP is like not the best, right? Not the best inhibitor. If you have a bunch of AMP, ATP basically won't even be felt. And this makes sense, right? Because if you have a lot of energy, if you have a lot of energy, so a lot of ATP, you don't want to be making fructose 1,6-bisphosphate. Because that's how you'd be making more energy, right? You want to slow it down if you have a bunch of energy already. Likewise, if you're low on energy, right, you really want to speed this up, so you activate it with AMP. All right. Okay. So after the third reaction, we get the fourth reaction, which is the aldolase reaction. So we basically 4 here, and we take fructose 1,6-bisphosphate, and that, using aldolase, goes and it turns it into glyceraldehyde phosphate and dihydroxyacetone phosphate. So fructose 1,6-bisphosphate GAP, DHAP. All right, you split it into these two things. All right, GAP is the one that we want. DHAP is not the one that we want. All right, aldolase specifically, one of the intermediates, it has a covalent intermediate. Where the relevant part looks like this, where you have a nitrogen on a lysine, gets double bonded to the carbon with a carbon up here, and a carbon here, and then carbon here, and then carbon here, and then carbon here, right? And it splits 2 bonds away from the carbon that it's bonded to, right? So you have this bond here, this is bond number 1, and you have this bond here, number 2, this one gets cut, right? And then one of them comes out, the other one comes out later. So that is how aldolase works. And then after the aldolase step, we have the DHAP. So this is the 5th step. We have DHAP. We don't want DHAP, we want GAP. So we need to convert that D to GAP. And this is just through triose phosphate isomerase. Triose phosphate isomerase. Right, makes sense. These are both 3 carbons. So triose, they both have a phosphate, PI, phosphate, and they're isomers, so isomerase. All right, so now that we have 2 GAP, everything from here on out is going to happen 2 times. All right, we're only going to write it once, but it happens twice. So step number 6. Step number 6 is what we call the magic of glycolysis. It's where we take a GAP plus an NAD plus a phosphate, and then we turn that into 1,3-BPG and an NAD plus. All right, so we turn GAP into 1,3-BPG plus an NADH. That should be an NADH. And a proton as well, for various reasons. So 1,3-BPG, if you remember that in hemoglobin, right, we had 2,3-BPG. This is the same thing, right? Just with the phosphates in the 1 and the 3 as opposed to the 2 and the 3. Right, so exactly the same thing except 1,3 and 2,3. All right, this 1,3-BPG, right? This is a pretty high energy compound, right? So high delta G. We can use that 1,3-BPG plus an ADP. Oh, and the name of this is going to be glyceraldehyde 3-phosphate kinase? No, dehydrogenase, yeah. So glyceraldehyde 3-phosphate dehydrogenase. Okay, name makes sense, right? So glyceraldehyde 3-phosphate, that's one of the substrates, right? This has a phosphate on 3 carbon. It is a dehydrogenase because you're taking an NAD plus and turning an NA into an NADH, right? Anytime we deal with NAD plus to NADH, 9 times out of 10 it's going to be a dehydrogenase. And yeah, so name makes sense. It's probably the longest name that we deal with. Step number 7, right? The enzyme that does this is phosphoglycerate kinase, right? And what we get is we get an ATP, yay! And we get a 3-phosphoglycerate. All right, so we basically get rid of this one phosphate and put it on ADP. right? Simple as that. What is useful about this is because we get an ATP out of it, right? And because everything from step 5 onward is being done twice, we get actually 2 ATPs out of it. So we recovered our loss, and now we have 3 PG. All right, so now on 8 here, we take this 3 PG and we turn it to we equilibrium, turn it to a 2 PG. All right, and this is done by I believe phosphoglycerate mutase. Yeah, phosphoglycerate mutase. Mutase. All right, so phosphoglycerate mutase. The way that this actually works is that there is a histidine that is phosphorylated, right? It starts phosphorylated. You then turn 3-PG, you add this phosphate to it, and you turn it into 2,3-BPG. Oh, that's our buddy from hemoglobin, right? After you turn 2,3-BPG, then the 3-phosphate goes back onto the histidine to make it be okay. All right, if this histidine becomes dephosphorylated, you need to add back in 2,3-BPG to get this to work again. So there is a little bit of 2,3-BPG in every cell just to make sure that this phosphoglycerate mutase enzyme actually continues to work. All right, step 9. Step 9, we take our 2-phosphoglycerate, right? 2-PG, we take that and we go to, we turn it into phosphoenol pyruvate in an equilibrium through a enzyme called enolase. All right. It also uses a water to turn that, right? So you have phosphoenol pyruvate, you turn 2-PG into phosphoenol pyruvate. Phosphoenol pyruvate is the high energy compound that in step 10, we turn our last step of glycolysis and the third one-way step in glycolysis, you turn PEP to pyruvate. And in doing so, you take an ADP and turn it to an ATP. And you do this through pyruvate kinase. Now pyruvate kinase, right? It has a lot of little regulation going on with it. Not as much as fructose, as a phosphofructokinase does, but pyruvate kinase, so it is inhibited by ATP, as you would think it would be, right? Anything that furthers glycolysis is going to be inhibited by ATP. Makes sense. It's also inhibited, or no, that's the only thing it's inhibited by. But then it's activated by AMP. Makes sense. Low energy. You need to, get this done, right? It's inhibited by AMP, activated by AMP and fructose 1,6-bisphosphate. Why is it activated by fructose 1,6-bisphosphate? Well, going, all of these reactions from the phosphofructokinase down to this pyruvate kinase are basically required. They're all equilibrium reactions, right? They could go either way. And the way that they're pulled down this pathway is through this last step with a very large delta G. And if this enzyme stops working, right, the things will stop being pulled down the pathway. And so we want to make, if there's a lot of fructose 1,6-bisphosphate, which is the last regulation step before this one, right, we want to get all of that down to pyruvate so we can keep stuff flowing through the mechanism. And that is glycolysis. As net, we have 2 NADH made. We have net 2 ATP, right? We got 2 from the step 7 where we converted 1,3-BPG plus ADP to ATP and 3-PG, right? We did that twice. So we got 2 ATP from that step, and then we did 2 ATP from this last step where we convert phosphoenolpyruvate to pyruvate and ATP. And we do that twice because we have 2 PEPs per glucose, and so we end up with 2 net ATPs. Now, the ATP, yay, that's fun. Cell will use that to do stuff. But this NADH is annoying, right? So if you don't get rid of it, it's gonna end up basically making this reaction right here, the magic of glycolysis, go backwards. Where you have NAD, where you take NADH and 1,3-BPG, right? You're gonna go backwards and make this, right? And so we gotta get rid of this somehow. And well, if you are aerobic, right, it's just gonna go to oxygen, right? You'll send those electrons in the NADH on oxygen, you'll make water, and it's great. Perfect, fine. You'll send it to the electron transport chain, and everything will be good. But if you don't aerobically respire, like the vast majority of organisms on this earth, well, I'm not sure if that's true. When the term radiolabel is used, so if you have like a carbon, you could have like a carbon 14 put into like a molecule of glucose, right? So you'll have like a C14 carbon, or oxygen, carbon, right? You'll do the reactions of glycolysis, and then it will end up at something like on a pyruvate with a C14 here, looking like this. And then C, and so you can like know where the where this carbon in particular on the glucose goes to in the final product. So yeah, so we got to get rid of this NADH, right? And so what we'll do with this NADH is there are 2 pathways, right? We have ethanol fermentation, which is everyone who's over 21's favorite, and then lactate fermentation, which we use. So let's start with ethanol fermentation. Right, so you take your pyruvate, so it's got 2 steps, right? You got your first step is pyruvate. You take this, this pyruvate actually looks like this. COCH3, right? If you have carboxylic acid next to a carbonyl, right, that's no good. The body's gonna get rid of that, and it does so via an enzyme called pyruvate decarboxylase, right? And this is a 1 reaction, and you'll see why in a second. So this is called pyruvate decarboxylase, right? So you take this pyruvate decarboxylase, you get rid of a carbon dioxide, and you get acetylaldehyde, which looks like that. Oop, it looks like that. All right. This acetaldehyde. You'll then take this acetaldehyde, and you will turn it into ethanol. So you'll add in NADH, and you'll get out NAD+. And this is through alcohol dehydrogenase. right? We talked about earlier about how anytime you have an NADH to an NAD+, you're likely going to have a dehydrogenase. This is another example of that. All right, and then you have lactate fermentation, which is a little simpler. You just have your pyruvate, O minus, C double bond O, CH3, right? Your pyruvate. This is actually an equilibrium plus NADH goes to form lactate, which looks like this. You have C, you have O minus, and then you have C, H, O, H, CH3. This is lactate. All right, so why do we do lactic fermentation as opposed to ethanolic fermentation? Well, ethanolic fermentation, right, you get this acetaldehyde, which you can use you can use in the Krebs cycle. This will basically get turned into acetic acid, and then acetic acid has some place in the citric acid cycle. But we use lactic fermentation because you can take this lactate in the liver, you can send it to the liver, add an NADH to it, you'll get back pyruvate. Pyruvate can then go all the way back to glucose. So we lose a lot. This is a lot more efficient than ethanolic fermentation. But if you don't have a liver to do gluconeogenesis, why bother doing anything but lactic acid fermentation? Also, if you were to do gluconeogenesis, you get back out this NADH, and you'd have the whole problem again where you have to get rid of the NADH. And so ethanolic fermentation is just easier because you can just make ethanol. Ethanol is not great, but you've gotten rid of it. But we can use the NADH to power the electron transport chain. So that's why we use lactic fermentation. Okay, we talked about the regulation of glycolysis. So now let's talk about fructose. So fructose metabolism, if you're in the muscle, then it's pretty simple, right? You just turn fructose into F6P with hexokinase, and then it just plugs right into glycolysis. If you're in the liver, you don't have hexokinase. You have fructokinase. So in the liver, it's a little more complicated. So you take fructose and you phosphorylate it with fructokinase. You get fructose 1-phosphate, which your body can't really handle with. And so there's going to be, and so you basically use F1P aldolase to split this up into DHAP and glyceraldehyde. The DHAP can just go to GAP and then fun time, right? But this glyceraldehyde has two steps. It can two pathways it can go. You can either take glyceraldehyde phosphatase, right? And that'll turn it into GAP. Or you can go use an alcohol dehydrogenase to form glycerol. This glycerol can then go to form lipids, or you can take it, you can phosphorylate that glycerol somehow, right, to form glycerol phosphate. Then send it back up here through alcohol dehydrogenase. All right, so you can set it back up there through alcohol dehydrogenase, and you lose an NADH here, but you gain an NADH here. So really there's no difference between these two pathways, but this pathway gives us the intermediate of glycerol, which we can use to make lipids as the backbone of our lipids. Okay. All right. We have the pentose phosphate pathway now. Okay, so the pentose phosphate pathway. All right, so we start with G6P here. All right, we then use G6P dehydrogenase, and we get out an NADPH, and we get this sort of weird structure called 6-phosphogluco 6-phosphogluco delta lactone. Complicated name, I don't like it. But we get out that structure, right? And that structure ends up being turned into you get rid of another NADP, you get another NADPH, right? And that ends up getting turned into ribulose 5-phosphate. All right, that ribulose 5-phosphate can then be turned into either xylulose 5-phosphate or ribose 5-phosphate, which that ribose 5-phosphate can then be taken to term nucleic acids. Okay, and then I believe it is 2-xylulose, so 2X and 1 ribulose come together and through a series of reactions where you have transketolases, which move 2 carbons. Transaldolases move 3 carbons. Through a series of steps, you end up with a GAP plus a fructose 6-phosphate. Both of these can then go plug into glycolysis. Or gluconeogenesis. Right, so all of this is reversible. You could, in theory, take these, all of it's reversible except for this step right here, for phosphoglucodelta-lactone. This, you end up losing a carbon dioxide. And so this step is not reversible. This step is not reversible. Well, this step is reversible, but not in our bodies. So this step is not reversible. This step is not reversible. All right. And so we end up with basically That is our pentose phosphate pathway. You can end up, you get 2 NADPH per run through of glucose, but 3, or sorry, you do that 3 times, right? Because you have to make 1 xylulose 5-phosphate, 1 ribose 5-phosphate. You have to do that to sorry, you get 2 F6P and 1 GAP. I forgot that. Okay. You get 2 F6P, 1 GAP from it, and they can go to glycolysis or gluconeogenesis. You have to do this 3 times. So every output here, you've gotten 6 NADPH. All right, by removing 3 carbons total. All right, if you did this fully, right, for a full amount of glucose, so 6 carbons, you would get 12 NADPH. And by getting rid of 6 carbons. Now, if you're making fats, that's really useful because these are used to make fats. But yeah, these are used for reducing power, and fat synthesis needs reducing power. Okay, so we did that. Okay, gluconeogenesis. Yay, gluconeogenesis. Right, this is backwards glycolysis, but backwards. All but 3 steps were equilibrium, right? And so we don't have to worry about 3 steps. The first step we want to worry about is the pyruvate to PEP, which actually the way we deal with that is we do a sort of step intermediate. We turn pyruvate into oxalo OAA, oxalo. How do you call it? Oxaloacetate. That's what we call it. For this, we use pyruvate carboxykinase, or yeah, carboxylase, which uses an ATP, and this enzyme right here actually uses biotin, which if you remember that mechanism from in class, that was hell. I believe biotin looks something like, you have like basically a cyclic urea, and with another thing down here, and a cyclic thioester below that. And then it's connected to basically a lysine. Yeah, it's connected to a lysine there. The nitrogen on the lysine, right? And so that's biotin. It's needed for pyruvate carboxylase. There's a whole mechanism we went over about how it works, but I can't see him asking any questions about that. Yeah, I cannot see him asking questions about it. One thing is that, okay, so then oxaloacetate then goes to phosphoenolpyruvate with just something called PEP, carboxy kinase. This reaction right here is notable for needing a GTP, so you lose a GTP there. But if you remember the nucleotide reaction thingy, losing a GTP is equivalent to losing an ATP as far as we're concerned. And also goes a CO2. You also lose a CO2 in that reaction. So another thing, right? Oxaloacetate is present in the mitochondria, right? And so you may want to put, but gluconeogenesis occurs in the cytosol, and there are no OAA translation proteins. Transfer. Right, so no oxaloacetate transfer proteins. This, what this means is that we have two ways to get it out of there, right? We can turn oxaloacetate into malate in the malate shuttle, which moves reducing power. And then we have the aspartate shuttle, which doesn't move really anything of importance. It moves an amino group out. So if you need reducing power, you'll do the malate shuttle. If you don't need reducing power, you use the aspartate shuttle to get oxaloacetate out of the mitochondria. So yeah, let's go. And then the rest of the reaction we have to get around are really, really simple, right? 2 and 3. Basically, we have G6P to glucose and F16 bisphosphate to glucose, or to F1P, right? We just add a water. There's not really anything to it. This is done by G6Pase, I believe. So glucose 6 phosphatase, and this is fructose 1,6 bisphosphatase. So nothing really there. When it comes to the regulation of this, oh, and the G6Pase, right? You typically only really find this in the liver. Because liver wants to keep making glucose, right? But the rest of it doesn't. Muscles and like regular cells are just stored as glycogen. And to be glycogen, you want it to be G6P as opposed to just regular glucose. Okay, but FBPase, right? This is actually inhibited by AMP. Makes sense. When you don't have a lot of energy, you don't want to spend, you don't want to get rid of something that will give you stuff. That will give you energy. You want to keep around the fructose 1,6 bisphosphate. And it is activated in the liver by citrate. Citrate is the carboxylic acid cycle. It is an intermediate in that, and if it's present a lot, then you don't want to be doing a lot of. Then you want to be storing more glucose because you have a lot of citric acid stuff, intermediates, anyways. So you don't need to be making more, right? So high energy, you want to activate the stuff to store. Low energy, you want to deactivate the stuff to store. Okay. Then there is also fructose 2,6 bisphosphate. And I forget what's useful about it. Okay, so there is a molecule called fructose 2,6-bisphosphate. All right, fructose 2,6-bisphosphate. What it ends up doing is it activates PFK, phosphofructokinase, which turns fructose 6-phosphate into F16BP, and then deactivates the FBPase, which goes the opposite direction, right? So fructose 2,6-bisphosphate helps push the push glycolysis along. The way that the enzyme that actually does it, it has two active sites, right? And it catalyzes both ways. One active site catalyzes one way, the other active site catalyzes the other way. We call it PFK 2 FBPase 2. All right. If it is phosphorylated, then FBPase 2 is active, right? So when this is phosphorylated, this is active. If you get rid of that, then this is active. All right, and this is actually controlled by protein kinase A. All right, protein kinase A will phosphorylate or dephosphorylate those enzymes, or the enzyme, depending on what signals it's getting from the outside body. Basically, the way it works is we have a sort of receptor on the outside here that gets glucagon, right? Then that glucagon then sends a signal to the protein kinase A. Adenylene kinase. Adenylene kinase, which then turns ATP into cyclic AMP. That cyclic AMP then goes as a secondary messenger. If you remember from Dini's class, secondary messenger was like the first thing we covered, to activate protein kinase A. All right, so protein kinase A is activated, then, excuse me, let me look for that page. So protein kinase A is activated. Then we end up with the enzyme is phosphorylated, and we store more glucose because we do gluconeogenesis. All right, a little bit more, let's go. Okay, so now we have to talk about glycogen, right? Glycogen has alpha 1,4 linkages and alpha 1,6 linkages, right? The alpha 1,6 linkages create a branch. The alpha 1,4 create the stem, right? So we get a bunch of alpha 1,4 linkages right here. So horizontal are alpha 1,4 linkages, horizontal lines are alpha 1,4 linkages. Vertical lines are alpha 1,6 linkages, right? You get a structure of glycogen that looks like this, right? There are actually 3 enzymes that deal with glycogen breakdown. So our first glycogen breakdown enzyme is called glycogen phosphorylase. So glycogen phosphorylase. All right, it turns glycogen plus PI into, so glycogen with N substituents to glycogen minus 1 substituent plus G6 or G1P. All right, we then take this G1P. So speaking in this reaction, right? You need a vitamin B6 to have this work. And the delta G standard is basically 0, but there's so much more phosphate in your cell than like glycogen that it tends to go this way, right? So even though the delta G standard is close to 0, there's so much more phosphate that the concentration of the enzyme or the concentration of the substrate pushes it this way. The Chatelier's principle. So one more thing about this, there's this little cleft that can fit about 4 to 5 glucose in that are alpha 1,4 linked, right? So part of this part of the stem, but cannot fit an alpha 1,6 linkage. Okay, and so what you end up with is you end up with a glycogen that looks like this. It goes along, goes along, goes along, goes along until eventually it gets to the point where it has only a few more left, right? And then it can't cut those anymore, right? And so there is an enzyme called glycogen debranching enzyme. So glycogen debranching enzyme. All right, so this glycogen debranching enzyme, what it'll do is it'll take all 3 of these, or it'll take all 3 or 4 of these, right? And it will throw them on the end of this longer trunk. So you'll end up with a very short, you'll end up with a 1,6 linkage, and then a longer 1, 2, 3, 4 tail. All right, and then now we have to get rid of this right here. And the last thing that we deal with for that is we actually just hydrolyze this bond. So we throw a water in this, and then we get out plain glucose. No G1P or anything like that, just plain glucose. So yeah, and then the final enzyme we need, right? Because we get G1P, but not G6P. And that's not good. So we have G1P, right? We just have an enzyme called what is it called? Phosphoglycerate mutase. Phosphoglycerate mutase. Okay, and that converts G1P into G6P. And the same mechanism that the phosphoglycerate mutase enzyme did earlier, where it phosphorylates the histidine and then creates the double phosphorylated intermediate, and then finally kicks it out to the G6P, restoring the enzyme. All right. Okay, so we have regulation of glycolysis, which has phosphorylase. phosphorylase B and phosphorylase A. They're the same enzyme, except phosphorylase A has a phosphate group on it. Only difference between the two, right? If you throw a phosphate group onto this one, then you'll turn it into phosphorylase A. If you hydrolyze this phosphate bond here, then you'll get it to be phosphorylase B. So really easy control. And phosphorylase B stabilizes the T state. So the phosphate stabilizes the T state of phosphorylase B. And then the R state is stabilized by phosphorylase A. All right. So the T state is stabilized by ATP being present, G6P being present, right? If we have too much G6P, right, we don't want to be doing this reaction. And then also glucose being present. And then the R state is stabilized by AMP and the enzyme being phosphorylated, right? So the little PI there, RPI, right? Now that's in the liver. In the muscles. That's in the liver. The main thing is just this glucose, right? So liver really cares about you having glucose as the inhibitor. It doesn't really care about the being phosphorylated, activating it. All right, and that is it to where we have covered so far. I think we have glycogen synthesis left in class, and that's it. Okay. So take a look at the exam. Okay, I have that printed out here. So if we take a look at the exam here, if you want to give you a minute or two to go to Blackboard and pull it up, if you don't have it printed out. Okay, so this exam here, this first question, right? Calculate the standard free energy change of an equilibrium constant for phosphoryl group transfer from 1,6 bisphosphoglycerate to ATP using the table below. Okay, so you're sending it from 1,6 phosphoglycerate to ADP, right? So this reaction we care about right here, and this reaction we care about right there. All right, so we have 1,6 phosphoglycerate to ATP to ADP, right? So ATP to ADP plus PI, that is negative 30.5. But we're going to go the opposite direction. So we're going to do ADP plus PI goes to ATP. And that is going to be positive 30.5. All right. Then the 1,3 bisphosphoglycerate. So we have negative 49.4 plus 30.5. That gives us something. I don't have a calculator on me. That's fun. Desmos to the rescue. Desmos. Desmos is fun. We love Desmos. Okay, so negative 49.4 minus or plus 30.5 gives us negative 18.9 kilojoules per mole. All right, then with the kilojoules per mole, right? So once it's calculate the standard free energy change, which we did, and it also wants to calculate the equilibrium constant. Well, if you remember, the delta G not standard is equal to negative RT natural log of KEQ. Right? Remember that last year? It's still relevant. So delta G is equal to natural RT natural log KEQ. Did he tell us the temperature? No, so we assume that it's going to be 25 degrees Celsius. So 25 degrees Celsius plus 273 Kelvin, right? That times 8.3145. Well, actually, hang on. We got to rearrange this equation here. So we have natural log of KEQ is equal to delta G not standard over RT, negative that. And then KEQ is going to be equal to E to, we're going to say that's A, E to the A. All right, and so whatever that is, so we have our negative 18.9 kilojoules per mole divided by, positive 18.9 kilojoules per mole divided by 8.3145 times 10 to the power of minus 3 times the temperature, which we're going to assume to be 298, gives us a KEQ of 7.63. So those are two equations, right? This one, and then adding up unfavorable reactions to favorable reactions. All right, so that's for question 1. Yeah, okay, that's for question 1. Now for question 2. If glucose is labeled at the C6 position with C14 passed through glycolysis, which carbon of the pyruvate will you find the with the radio label we found? Okay, so this one, right? So we stew it. So glucose looks like, I'm going to ignore the OHs and this. So this is going to be C14, right? C14 here. This top carbon here. If we remember, whenever we have the aldolase step, the aldolase step converts you into GAP and DHAP. And it is phosphate. Okay, so it's going to be the third position of GAP. Because so you get DHAP, which is like this, and this, with the phosphate on the first one, so PI there. This is DHAP, and then GAP, you have 1, 2, 3. I believe this is an aldehyde here, glyceraldehyde phosphate, yep, okay, and then OH, PI, okay. Carbon 1, carbon 2, carbon 3, carbon 4, carbon 5, carbon 6, from GAP to DHAP. From glucose all the way here. So this is carbon 1, 2, 3, 4, 5, 6. All right. So the carbon on the carbon on carbon 6, that is going to end up being the, so we do that, and then 3PG to 2PG, and then phosphoglycerate mutase goes there, and then enolate. Yeah. Okay, so this is going to be so pyruvate looks like this. OCOH3. This is carbon 1, carbon 2, carbon 3. Carbon 6 will be this carbon right there. So this will be the C14 one on pyruvate. So I guess if we want to sort of go through this entirely, We'll say that for next time, actually. Yeah, we'll save solving this in general next time. Yeah, it'll be on carbon, the methyl carbon of the pyruvate. All right, if the pyruvate were made back into glucose by gluconeogenesis, where would the radio label be found? Okay, so if we think about the reactions to go backwards in glycolysis, we make an indoxyl acetate and add the CO2. Yeah, we add the carboxy group. Backwards. Come on. What's the mechanism? Fuck. You add. Okay, so we have that. Goes out, and then it looks like in the first step, so we go pyruvate, right? And then we go OAA, adding a CO2 basically, and then we go OAA to PEP, losing a CO2. It looks like in that step, it looks like in that step, it is the same carbon dioxide being added and lost. So we're not losing anything there. Okay, and then the other two steps of gluconeogenesis aren't a big deal, but so we convert pyruvate back into like GAP, for example. We convert it back into GAP. It'll be on the last carbon of GAP, right? So here's GAP, C, H, C, P, I. So it'll be on this carbon of GAP, but if it gets converted back into DHAP, then it'll be on this carbon of DHAP. So PI, carbon, carbon, it'll be on this carbon of that one. And so it'll end up as either carbon 1 or carbon 6. Again, I think that's correct. We'll go more in depth into it next time because I'm kind of losing steam right now. And with that, I think we're probably going to end this session. All right. Y'all have a good one. Be safe.